Hi, well, today's video is looking at constant angular motion. Let me jump to a little animation to start off. So I'm just going to run this play. We have a little ladybug that's moving along in a circle. And so as you can see, this ladybug moving along here is moving at a constant speed in a perfect circle. Let me take a quick screenshot of this ladybug. I'll just maybe pause it at some point, like right here, for example. Okay, I've just pasted it in here. And I'm going to maybe just show a few things here. Let's say that we have an x-axis here and a y-axis here. We can kind of label this. This is my y-axis and x-axis. And let's say the ladybug started here at point P, and then at a later point here, it's at point Q. All right, so we're going to define a few things. This distance right along the path that it takes, this is what we call the arc length. That's S. This is known as the arc length. All right, and then this distance, maybe I'll just make it dashed here, it from the center here, which is what we call the axis of rotation, all right, to the point P or Q is known as the radius. And, or right radius, I guess, out as well. And then this distance in here, this is the angle. Theta is known as the angular displacement or angular position, if you'd like to call it. Okay, so delta theta would be basically angular displacement. Okay, so this is kind of summarized in my notes. So I'm going to turn to that now. All right, and you should have been given the notes earlier in class. So previously, in our last class, we quickly learned about terms like position, displacement, velocity, right? And we were only looking at things that are moving in a straight line at constant speed. All right, now we're looking at things that are rotating at a constant angular velocity. So we're going to be looking at the rotational version of all these things, like angular position, angular displacement, and angular velocity. So when we're looking at an object that's moving in a circle, it could be like a figure skater that you see over here. You have an axis of rotation, or it could be a Ferris wheel going in a circle and you have an axis of rotation. All right, now it can be accelerating, but we're not looking at this at this point in time. We're only looking at things that are moving at a nice constant speed. So as the disk, for example, over here rotates, as I mentioned earlier, here's the radius, there's the angle that it goes through, and this is the arc length that's along here. All right, so as we look at point P and it moves to C, there is a relationship between the arc length S, the radius, and theta, and that is shown right over there. All right, S equals R theta, and that's something you might have been introduced to in math class. All right, S is known as that arc length. It must be in some units of like meters or centimeters. And radius, again, I would typically put that in meters. And then your angle, now that's where it's different. We're not using degrees. It must be in units of radians. So hopefully you're all familiar with radians. When you go in a circle, just to recall, if you go around one complete circle, that's 360 degrees is basically one revolution. We know that as 2 pi rads. So hopefully you've learned that. 2 pi radians is equivalent to 360 degrees, or pi radians is equal to 180 degrees. Or if you'd like, 1 radian is equal to 57.3 degrees. So this relationship you're going to be using in some of the problem solving. Moving on. Now, we're making the assumption that this object is moving at a nice constant speed. So there is a constant angular velocity. So this is a new term. I'm going to scroll down to the notes here. Angular velocity. The symbol we use for angular velocity is looks like a W, but it's actually technically called, in Greek, that letter is called omega. It's not the capital omega, it's the small version of that, the smaller letter version. Okay? And so the angular velocity is given as the rate of change of the angle over time. So this equation right here is really important. Okay, we're going to be using that. The units of angular velocity are in radians per second. Okay, you might have heard of other types of rotational speeds like revolutions per minute, known as RPM. A revolution per minute, by the way, is like 2 pi radians because you make one revolution is 2 pi radians. And then in a minute, you have 60 seconds. So if you want to convert an RPM to radians per second, you would multiply by 2 pi and you would divide by 60. So we do have a sign convention because just kind of like, you might assume like right on when we did linear, we used to maybe assume right is positive and left is negative. Same idea. We need to have some kind of like, what we define as positive. So when, as you saw in the animation earlier, you saw the ladybug was rotating in the counterclockwise direction. That is assumed to be positive. If you rotate in the clockwise direction, that is assumed to be negative. So that's our sign convention we're going by. Okay, moving on to our next page of the notes, we have also a little bit about the relationship between the linear velocity, or sometimes called the tangential velocity. That's essentially like how fast you're going. And how is that related to the angular velocity, which is kind of shown over here? That's that kind of arrow over here, just telling you how many times it's rotating per second, or what's the radians per second. So maybe you've heard of this. If you're further away, then the faster you're going, right? There's a relationship between the speed, angular velocity, and the radius. And here is the formula. So v, the tangential speed or linear speed, equals the radius multiplied by the angular velocity. So of course, if you have a point here like Q, it's going to be going slower than point P. P is going faster because it's further away. Okay, so that's my brief summary on the equations, the mathematics of moving at a constant angular speed. Now let's put it in practice and do example number 1.